Hi everybody. This patient just appeared at my doorstep with a simple message, please fix me. I didn't know what to expect or how to return the package, fixed or not. But the curiosity is strong with this one, and it always has been. The label says oil pressing machine, which goes by the brand Yoda. Well, that happens when you let the nerds to pick up the name for your product. The control panel reveals that it's for pressing oil out of seeds. There is a bunch of programs for different kinds, and the machine probably alters the process based on the type of the seed. The machine is pre-disassembled, so we can check the innards directly. There is a hopper of some sorts, which probably accepts whatever you want to turn into oil. That falls into this metal casing, and by the looks of it, the pressure is created by moving the matter to the dead end of a shaft, compressing it, and since it has nowhere to go, the oil is drained out, leaving a dry slush in the tubing. There are small slots in the tubing where the oil goes, just dripping away into a container. The movement is done by a helicoid axle to produce torque. The motor is connected to the axle via angle gearbox, and there is most probably a worm gear, with something around 1:10 reduction creating the mechanical advantage. To make the oil draining more effectively, a higher temperature is needed as well, and we can see some heating element. To aid the seeds to go down the hopper, there is a small pedal operated by a stepper motor, which seems to be a bit overkill. The speed of the motor doesn't have to be regulated, I think, but it has to be quite low. Using small DC motor would require a gearbox since those things turn pretty fast, so that's probably the reason the stepper motor is used. As I said, I don't know what is wrong with this one, but let's disassemble it as much as we can and maybe the problem will pop up during the process. The enclosure is divided into top, side covers and main structure. That's the black plastic part. There is a bunch of cables zip tied to a mounting features of the main structure. One of the cables goes directly into the metal casing, and it looks like a temperature probe. Gotta be careful with this one, the wires are usually fine stranded with very few strands and tend to break easily. From the top cover leads another cable to the edge of the hopper, and that's a safety switch for the lid, so the machine will not start when the lid is not on. I'll try to free the PCB to have a closer look at that. Okay, let's break down what's going on with the printed circuit board. Starting with the power section, we can see a massive filtering consisting of capacitors, coils and varistors. Those are for suppressing high inrush current which is generated when the cold device is connected to the power line, and also for suppressing the electromagnetic interference generated by the machine. Then there is a small detour to the more dense part of the PCB. A diode, FET resistor and capacitor are combined into a simple rectifier which probably feeds tens of volts to the small switching regulator, creating a voltage for the digital section of the circuit. There is also good old 7805 near the connector which goes to the front panel, creating a filtered 5 volts. Next to it we have optocouplers which galvanically isolate the digital signals to and from the front panel from the rest of the system. The PCB under the optocouplers is coated with milling machine to provide extra isolation. That's a nice touch. Next to it we have connector called step, which goes to the stepper motor in the hopper. It is powered by ULN2003, a widely used transistor array, which is basically a power amplifier for low voltage signaling. The stepper motor cannot be fed directly from low power pins of microcontrollers and needs such buffer. Next to the microcontroller we have a connector called a Hall, and that's when things get interesting. This connector is one of two which goes to the motor, which is a 3-phase DC brushless motor, and the Hall connector is actually for Hall effect sensors which are in the motor. These sensors are typically used for measuring a magnetic flux. They are used for measuring RPMs of motors, where they are sensing a passing magnets glued to the rotor. Or they can indirectly measure a current flowing through the wires by measuring the magnetic flux which flows around the wires, and it is proportional to the amount of current. So what we are dealing with is a variable frequency drive with a feedback. The controller board needs to generate a 3-phase voltage, and the feedback is for detecting whether the motor actually turns. The controller can change the voltage amplitude based on the actual position or speed of the motor. To create a 3-phase system out of single phase, we need to rectify it first. Diode array in Gratz configuration is typically used for that, and by the 4 leads which pop out under the heatsink, that looks like it. Then the voltage has to be smoothed out, and that's why there is this big 350 volt 330 microfarad capacitor. After this capacitor, the control system has around 320 volts DC to work with. By the number of leads which goes to the motor, there is 3 of them, it looks like the coils are in delta configuration. To create a rotational movement, the coils has to be energized one by one in a given order, very similar to the stepper motors, with one exception: the current has to be alternating. The variable frequency drive does exactly that. The 320 volts DC created by the rectifier are applied to the coils. To create smoother transitions, the DC current is chopped by the high frequency PWM generated by the microcontroller to recreate the sinusoidal alternating current. And we are talking about tens or maybe lower hundreds of kilohertz. This fast connecting of coils to the power supply is done via transistors, possibly MOSFETs or IGBT. As we need each motor coil junction to connect to the both positive and negative, we need 3 couples of transistors, and those are hidden under the sink as well. They act as switches and generate heat when the current is flowing through them, which needs to be dissipated. This PWM chopping is also the source of the electromagnetic interference, which the massive filtering is trying to suppress. And last interesting part is the driver of these transistors. That's the chip covered in this gummy thing. Since the driver is constantly switching high current back and forth, it produces small vibrations which could result in chip just falling off the PCB. So this soft gummy glue acts as a damper. Let's continue with the demolition, shall we? With the PCB out of the way, I will remove the other components. The heating element is embedded in the metal casing, and it is quite interesting how that part has been manufactured. The heating is done by a wire, which resistance is set to the wattage it has to produce in heat, and by the label that is 350 watts. It is wired through the round sort of channel in casing, and then a liquid ceramic isolation has been probably poured down the channel as well. At least that's how I think it happened. Let me know in the comments how off my guess is. In the path of the current there is a temperature fuse which protects from overheating. Basically, when the casing gets too hot, it will break the current flow. Some of these fuses are resettable when they cool down, but I don't think that's the case here. When this one breaks, it needs to be replaced. This transformer looking thingy is directly in the line of the mains voltage, and by the number of leads is not a transformer, but a coil. Just another part of the elaborate EMI filtering. The variable frequency drives are notorious for excess EMI that they generate, and for household items there are strict rules of how much that can be. Otherwise they will not be certified and therefore not eligible for selling. Interesting is how jerry-rigged the coil is to the main structure. There are mounting holes for the coil, but the coil doesn't fit. These holes were probably for older part, and this is a replacement part. Something like that can happen during the lifetime of the product, and changing the injection mold to fit the new part, well, that's the last thing you would like to do. Freeing the motor and the metal casing is a bit of a hassle, and I need to take out everything to get the motor out. So far, I didn't find anything suspicious that would point in the direction of what might be wrong with the machine. And I hope it's not something on the PCB. But once the motor is out, it is pretty clear what the problem is. When the motor is manually turned, it stucks not even after one full revolution. The problem can be in the motor, in the gearbox, or in the shaft. After removing the shaft, the motor turns freely. That means the problem lies in the shaft with the helicoid axle. Well, that was pretty fixed together. The brown slush coming out are old seats, so the machine is just due with maintenance. And speaking of maintenance, the remnants of the oil are just everywhere, so I'll try to do the best cleaning that up. I tried using degreaser and even soaking up the parts in the isopropyl alcohol overnight, but none of that really helped. So I just scraped away mechanically as much as I could. Now it's just a matter of time putting all of that together. So it does produce oil after all. Good machine.